Okay, we can start. So welcome. It's kind of unusual because this is an honor section which is taking place before the main class. So, but hopefully you are all the smarter batch of students, so I can dive into some of the things. But really, this thing will start from next week. Okay. Anyways, let's. So by way of introduction. It's my name, Manish Srivastava. I know some of you may have seen me. My lab, whenever you come to Bolter Hall from the southwest corner, my lab is the one right opposite the elevator, Network Embedded Systems Lab. So I work on digital systems, computers, which interact with physical world, with humans, sensors, actuators, algorithms behind it, particularly things like machine learning algorithms and sensor processing type stuff. So that's what I do. There are two TAs in this course, so I partly wanted to take the opportunity to introduce them also. So Julian, who's there, Julian Di Gortari Brissino. Those of you are in Thursday, and which one on Friday? The first one? The first one? Okay. So the Thursday and the first Friday discussion section on Friday. If you're on that, he's your TA, and Jicheng, he's the TA for tomorrow and the second session on Friday. Okay, so that's a change. Apparently, that's how the assignment is. So Jicheng also works on digital systems at Professor Leha. His full name is Jicheng Ha. And so both of them have good computer engineering background, and also you're kind of in good hands. So what this section is about, hopefully some of you got a chance to look at the syllabus that I posted, and if you did, so kind of the idea is that M16 covers the main, like how do we design digital systems and all, but we kind of use, if you may, approaches which are more education oriented. So we kind of don't go with tools which are more how you design things in a professional setting. Whereas in M89, what we do is we expose you how these things are designed, the way if you were to be doing research or in industry, in particular, using what are called as hardware description languages. So actually, just as a quick thing, how many of you are like, do you know programming? Can I safely assume that everyone? Okay, because essentially, I don't want to teach you what is essentially a parallel programming language or concurrent programming language if you are uncomfortable with sort of opening programming. So hardware, you can think of it as when we describe hardware, we are really describing computation running on lots of tiny, simple pieces of hardware. So when you write a program in C, C++, we either write it for a processor, which is just doing one thing at a time, or maybe occasionally you write things with multiple threads. But here, one way of thinking about hardware is as if it's literally lots of tiny processors. So there are specialized languages, and Verilog is what sort of in this section we'll cover. The other thing, which again, when I go over the grading part in M16 later this afternoon, we'll see that. But basically, so kind of every assignment will have kind of an honors component, which essentially exposes you to Verilog. But then additionally, we expose you in as part of the honors program also with mapping things to real hardware. So there's a type of hardware called FPGA, Field Programmable Gate Arrays. So you're going to map stuff to that. So what? My sample. Kind of a little board. If you have ever worked with things like Arduino and all, it's kind of no different, except that instead of a processor, it has a FPGA. Okay, and there is a little sort of keyboard kind of thing attached to it. So you kind of map to that. And then finally, I'll sort of describe a little bit more in detail later. I also give you an option that if instead of taking the main courses, take home final, if you want to do a more researchy project as part of the honors thing. So in lieu of that, you kind of do that. few different ideas. I'll talk about it when I come to that slide. So this lecture, I just wanted to give you a flavor of how digital systems are designed. Now, unfortunately, if you don't know anything about what digital systems are, you'll learn in today's lecture later on. My apologies, but that's how the timing has worked out. But all of you have at least used digital system. Think of it as something which processes digital information, takes bits in, processes them, produces bits out for any number of purposes, whether to display to you on a screen or to send commands to some other computer or to, let's say, engine of your car or stuff like that. Okay, so that's what we'll do. Now, before I dive into the lecture, since it's such a small group, so it kind of reminds me of like when I was doing my undergrad, a lot of my classes were literally like sub 10 people. We are kind of pampered. So I want to just go around and maybe all of you can at least introduce you to me, but if perhaps not all of you know each other, so that would be good also. I am assuming all of you are ECE students, fast track students, presumably. So just, yeah, let's just go around. You probably know each other, but it would be good for me to know. So maybe you can start with you.
I'm Arsh.
Arsh.
Yeah.
Okay.
Fast track.
What, first year, second year?
First year.
First year. Okay. And where are you from?
Like,
California?
Yeah.
Okay. Fresno. Okay, cool. Welcome.
Hi, I'm Seth. I'm
Okay.
a CE fast track first year. Yeah, I'm from Irvine.
I see. Local. Okay, almost. Are you CE or EE? EE. Okay. Cool.
JC at first year fast track EE from the Bay Area, so 3-1.
Okay, cool.
I'm Bhavik. I'm a third year computer engineering major from the Bay Area.
Why are you taking it now? I mean, I'm confused. I mean, haven't you taken it before? No.
I took M16 last winter, but this wasn't offered the 89.
So you are just doing the 89.
Yeah.
Wow, I didn't even know that was allowed. Okay. Okay, so and you took it from me, I recall, right? I mean, yeah. So you'll still have to do the I guess the homework should be familiar to you, unfortunately. Maybe you should attempt doing something more researchy. I know you have been doing research. Okay, so yeah, just aim high. Okay, that's kind of purpose.
Hi, Isabella. I'm also third year EEBC fast track, and I took it last winter as well.
From me. Okay, apologies. Okay, so both of you are okay.
I'm Leah. I'm first year EE fast track in
Dallas, Texas. Cool. Welcome to the coast. Yeah. And you are?
I'm Gina. I'm a first year fast track EE student.
Okay, so we have a healthy number of first year and I guess almost graduating. Okay. Great. So I think last time I taught an honors section because it was offered during spring was in 2020, which was quite some time ago, I guess, and towards the end of it was the well, we just started on the pandemic sort of oriented thing, so it was all remote. So actually I'm teaching this thing in person, an honors section for the first time. So we'll see how it goes along, because I'm kind of modeling it after that one experience. I'll probably have to sort of wing it along the way a little bit. I also hope, actually, just another thing, how many of you are engaged in some sort of a research group? I know Bhavik is. Anyone else? Like, are you engaged in it with any professor doing any research stuff? No. Okay, cool. You can think of it also as something that maybe starting something which helps you engage in some sort of a research experience. In our program, as you know, we also have a honors thesis now, and consider doing that. I have one student doing it. I think he really loves it to the extent that he wants to stay on as a PhD student. So make use of these experiences. Okay, anyway, so let's start. So while this course is kind of has the perception of, and rightly so, that it's about hardware, but I really want to sort of think of it kind of a level above, right? We design systems as computer engineers. Those systems have some functionality. We are given some sort of a specification, right? Some input data coming in. If it's not already digital, if it's analog, we use something to sort of map it into digital. What do we use? Anyone? Like, how do we convert analog information to digital information? ADC, right? So ADC does two things. It discretizes in time, like it samples the signal. Some of you may have heard of Nyquist sampling, for example, right? Essentially, kind of the idea is I can take a continuous time signal, sample it at certain specified rate, and then there are theoretical frameworks like Nyquist sampling, which allow you to reconstruct the signal. There are better ways of doing it now, but that's a century-old way of doing that. And we also discretize it in value. So because we are dealing with real numbers, and of course, we have to represent them in finite number of bits, some finite sized entity. So we may divide, let's say if its incoming signal is air pressure, we can just discretize it into bins, and then let's say divide it into 8 bins, 3 bits. That's my digital value. So I have sensors, and ditto for actuators. Actuators is the reverse direction going to the analog world. And as I suspect, usually we drive it through some form of a digital to analog converter. They're called DACs. There are human interfaces. We interact with them. You can kind of think of them in the same way as physical world, right? I mean, we are part of the physical world. So again, a lot of human interaction depends upon sensors, actually haptics and sound and generating imagery and stuff like that. Our system also oftentimes need to talk to other computers. They need to be powered up. But the middle part is what sort of we are interested in, which is we have some algorithm for processing that information coming in from sensors and humans and other computers, and then generating some output as a function of what came in and historically and presently, and then drive the actuators, give output nudges to the human or messages to the other computer. Okay. Now, this part you can abstract it away, bits in, bits out. How that processing is done can be done through a variety of ways. If you're doing CS31, 32, 33, then we write a program using CPUs or specialized processors like digital signal processors or application specific processors, and a variety of things and various degree of general purposeness, right? I mean, it could be an Intel processor, which is designed for like a jack of all trades. And then there are processors which are more specialized for some singular purpose. FPGAs and ASICs, on the other hand, is what we've been into the hardware category, where instead of having a processor which is executing instructions, we basically go down deeper down into the primitives, and we'll see that in the main course, but essentially primitives which correspond to logic operations. Simplest one would be things like AND gate, OR gate, things like that, but kind of more complicated things doing addition or subtraction or multiplication. And they are literally like hardware on pieces of silicon, and then we compose our algorithm in terms of that. So the same thing, let's say I'm trying to add up a bunch of numbers, right? On a CPU, it might look like a for loop with a variable in which I'm just accumulating those values. Whereas on a FPGA or ASIC, it might look like an adder hardware with our hardware to store the values, and then we are looping through it in hardware. Okay, but conceptually, it is really an algorithm being implemented either directly using the gates or indirectly using a processor, which in turn, of course, is built using those gates, right? So you can think of a CPU as a piece of hardware, and the algorithm it is running is take the next instruction, execute it, take the next instruction, execute it, and then we write a algorithm in terms of those instructions. So it just introduces one level of indirection there. So CPU itself is running the algorithm corresponding to what executing a program. Okay, so in this course, we are more interested in this end of the things. ASIC stands for application specific integrated circuits. You can think of it as I am designing something for a specific purpose. I don't know, let's say controlling steering wheel of a car, then that would be an ASIC. FPGA, and it's literally baked into silicon. You can't generally modify it other than maybe tune some parameters. FPGA, on the other hand, is a technology which gives you a whole bunch of uncommitted logic primitives and wires to connect them. And then instead of your language, the algorithm you write in a high-level language of some form, instead of mapping it into the instruction set of a CPU, you map it to those gates. So the process kind of is the same, right? I mean, in all these cases, we are starting with a high-level language, often the same language. How many of you have seen MATLAB, for example? Right? Okay, so MATLAB is what engineers like to use a lot to describe systems. And from MATLAB, you can go to CPU, you can go to DSP, you can go to FPGA, you can go to ASIC. It's a single entry point from which you can go to a lot of these places. Even languages like C or C++ or Python, there are sort of restricted subsets of them, which you can map to the hardware also. So the view I want you to take away is that there's just a spectrum of choice, right? I mean, totally hardware to kind of flexible hardware to specialized processors to more general purpose processors. And these are just 4 points. There are probably many, many, many others. And then any algorithm in general requires storing information, right? Either information from the past, right? Because oftentimes the action I take at the current time step depends upon not simply what the world is right now, but also what the world was previously. So that concept is referred to as state. We have to remember some historical values. In context of a program, these are static variables or variables which are in the global scope of your program. If you familiar with Python and C, it would be global variables or inside a function. Static, I don't know Java that well, but probably some similar analog. But some variables in a program remain alive, unlike variables in a program where you enter a function, you set those variables, you exit, those values are lost. Okay, so those are just during one run of the function. Whereas there are other variables which are remembered as long as the program is running. Now, one of the things about hardware or a lot of these systems is they run forever. If you think about a CPU, it's running a program which is never ending, right? The program it is running is fetch the next instruction, execute it, right? That's the lowest level program of a CPU. Likewise, a piece of hardware is, as long as it's powered up, it's doing something. So they need to store information. And so there are a variety of memories, as they are referred to, which help us do that. SRAM stands for static RAM, DRAM stands for dynamic RAM, and flash, I'm sure all of you are familiar with it. What's the difference between these? Well, SRAM is fast and power hungry and expensive, so they tend to be small. To store each bit, it needs many, many transistors on the silicon. So usually you will reserve it either if you need small amounts of memory or in a normal processor, caches where we store. What's a cache actually? Anyone heard about it? Yeah.
Maybe it's a way to store like frequently used information.
Yeah.
So
if a program is, let's say, spinning on a variable or an algorithm is going to repeatedly access some value, then we store it near the computing hardware. So SRAM typically is going to get used for purposes like that, right? DRAM is one transistor or literally like one transistor and a capacitor to store one bit of information. So DRAM is as efficient as it gets. And so this is what we rely on bulk of our memory. So those DRAM memory sticks that you buy to put into your laptop or computer, if you've ever sort of done that, or like, for example, if you look at like here about this Mac, it says memory. So this 64 gigabyte is what is referring to the DRAM. Okay, the cache is really going to be part of the processor. M1 Max is the name of the processor. I think it probably has, I don't know, a few tens of megabytes of cache perhaps, but DRAM is what gives you the big sized memory. Okay, then back out here, SRAM and DRAM, both of them, you power them up, they basically lose their content. Flash, on the other hand, is used for even denser, and very importantly, it's permanent. Okay, so if you want to remember things across power down thing, okay, as well as they're used to store the program itself in case of CPU. So we use flash. This is where you store your photos and things like that. So flash memory, nowadays you can probably buy flash cards which are let's say a few terabytes. I think I've seen 8 terabyte type flash memory for laptops and all now. They're super expensive, like 8 terabyte would be like $1,000 or something like that. But and then there is also hard drive. I've not listed it because it's kind of like outside server arenas in our typical thing. You're probably not going to be seeing hard drives increasingly that much. All our laptops and all are now flash based. Okay, so algorithm gets mapped into the spectrum of technologies. So the takeaway here is there are many ways of implementing an algorithm, right? I can implement it as software on some sort of a standardized digital computer. And you can think of it as, like I said already, digital computer is a piece of hardware which is running a low-level program whose sole purpose in life is get the next instruction, execute it, go again, get the next instruction executed, right? So we are just sitting on top of another low-level program now. So our real algorithm, the one which you're interested in, is running on top of this low-level algorithm, which the processor is running. Sometimes that low-level algorithm is mapped directly into hardware, and sometimes it in turn is written as a low-level software, which is often referred to as firmware or microcode, a variety of names there. So this is where, if I don't know, any of you ever played with, like, let's say Arduino, you must have done E96 probably. So hopefully you may have seen worked with some processor, but that's Raspberry Pi is an example. There are a bunch of these things, and of course processor on your laptop. Okay, so that's one. I can also, when it comes to implement our algorithm, instead of working with a processor, I can literally just buy specialized, like instead of using a computer like this or a desktop computer, I can kind of build my own computer. So we can buy boards which have processors on them and kind of put them into some sort of a chassis and make our own device and then map the algorithm on it. So that's how a lot of industrial automation and all is done that way. I can create my own board using off-the-shelf components. So that's a third strategy. You design your own PCB and you get these components that kind of I mentioned, all of these kind of things for your particular purpose, right? So standard computer boxed, make your own system by plugging in subsystems and some sort of a chassis. So kind of there are like many bigger PCs have these PCI slots, for example, where you plug in your cards. If you're using a discrete GPU, sort of they plug into these things. So that's an example out here. Custom board is you kind of make your own. Many research groups do it. And of course, if you're an Apple making an iPhone, you're kind of doing that. And then there is also create your own chip. And ASIC and FPGA are out here. And here what's happening is that instead of working at the level of boards and mechanical things, I'm working on top of silicon typically. And my palette is not CPUs and boards and all. My palette is logic gates and things which plop down on the silicon. So the generic term is often called cores. Cores are pieces of hardware which do some functionality. So oftentimes they may themselves be little processors. There are companies which in the business of selling you cores, which you can put down on pieces of silicon, and along with other type of stuff to make your own thing. So this is referred to as system on chip. So at some level, M16 and all is really kind of, like I said, residing in this bottom thing. That's what we are kind of seeking to do. And in this honor section, we are going to do the same, thing. So, for example, let's say, I'm sure all of you have at least some generic idea of what a neural network looks like, right? So artificial neural networks are designed using kind of these simple primitives, which supposedly mimic the neurons in our brain. So they're kind of artificial neurons, and their functionality mathematically is described along the following: that a single neuron takes a bunch of sort of, let's say, real valued inputs or integer valued inputs, multiply them with some weights, and adds them up, add a constant, and then subject it to some nonlinear function f. In the past, it used to be things like hyperbolic tan and all. Nowadays, it's kind of a sort of a function which is called a ReLU function. Doesn't matter. Point is, f is nonlinear. So this whole thing is really f of b plus sigma I1 to n xi wi, kind of that. Just so this is integrating weighted sum of the inputs with an offset fed into a nonlinearity, and the output is what we in neural network parlance call as the activation value. Okay, and that then goes to the next neuron, and so on and so forth. It's just an example of something one might want to do, right? I mean, nowadays we are living through the AI ML era, and almost everything is being done using some primitive like this, right? So this is kind of the new primitive of computing that has emerged. And when we say we train a model, what we are really doing is we are trying to learn the B's and the W's, okay, for every neuron in my system. And almost all neural networks are some permutation of this kind of a basic computation. So one thing I forgot to mention is that when we train, what loosely speaking, at least if you ignore for the moment the recent stuff which is happening, a classical way of training these things is we show it an input, and we also know the correct output, and we compare what output is being produced by my system, compute the error, and then based upon that error, we go back and adjust all these weights and offsets all through the network using kind of like, if my function is a plus bx and output has a little bit of an error, then I can sort of do a I can go back using the slopes and say, how much should I adjust A and how much should I adjust B? Okay, so that's the game that we play out here. So the reason I mentioned this thing is that I can implement this thing in software, sure, right? I mean, I can essentially describe a function and describe how the two things, how to do the computation and how to update it. Point I want to make is we can do the same thing in hardware too. And a lot of progress right now in kind of AI ML is really coming from development of hardware, which is specifically tuned for either processing the forward path of this computation, which is what we do when we are using a neural network, or doing the forward and backward path, which is what we need when we are training the neural network. Okay, so when we hear about how ChatGPT uses a model which requires like gazillion dollar worth of training and all, it's basically that's happening. So now even there, one common way of doing it is using the so-called GPUs, right? Because it turns out that GPUs are very good at doing lots of such computation in parallel. But there are also companies which are making specialized hardware, even analog hardware, where unlike this course where we are focusing on digital computation, there's also analog computation, which has emerged or has been revived. Computation used to be analog decades ago, and because of neural networks, we are seeing kind of a revival of that. So I can do it in software, or I can do it in kind of map this computation literally into hardware. I can think of it as I need a multiplier, bunch of multipliers. I need an adder, which adds them up, another adder to add B, and then I need some sort of a hardware to implement F. And that would be the hardware for a neuron. And then I need lots of these copies corresponding to what my neural network is. So I can take sort of variety of approaches for doing it. So if I'm doing it on a software, one very common type software that we of platform that we deal with is the processor that you find on our laptops and all. So like my laptop has this M1 chip from Apple. That's an example of what is referred to a microprocessor. Microprocessor in turn has kind of three types of things. It has some area where variables in a program get stored. When you say int x, it needs to be stored someplace. So now if we store it in a memory, then that would be very slow to access because you will have to travel to it. Just to put things in perspective, a big modern chip, maybe let's say 5 centimeters in length. Okay, how much is speed of light? Yeah. Huh? Say it again.
300 millimeters.
Okay, 3e⁹ meter per second, right? I mean, whatever that is. Okay, so 300 million. Yeah, you're 3,000 million. Okay. The point is, I was trying to make is that just for that tiny little chip, for information to travel from one part to another is a healthy fraction of a nanosecond. If you're going across a laptop like this, right, we're talking about tens of nanosecond or order of 10 nanoseconds. So information travels at a finite speed. So anytime you go outside, right, there you are paying a penalty for that. And moreover, all of your ease, information, this rate at which actually the signal travels over a wire is affected by its resistance and capacitance as well. So you want to keep information close, and therefore registers are implemented by a particular type of logic primitive so that it's kept on chip close to it. And a lot of games you can play. So if you come to storing information, if I go back to this hierarchy that I had before, you can say to the left of SRAM are registers. So registers are like super costly, super fast, can be on chip. SRAM, less costly, less fast, can still be on chip in modest quantities. DRAM, we can make in huge quantities, much slower, hundreds of nanoseconds type time to access. You may put it on chip in some cases, but pretty rare. And then flash is almost, again, you may put on a chip in some circumstances, but typically off chip. So registers. ALU is what's referred to as arithmetic logic unit. This is where the computation takes place. And control logic is the part I was referring to, get the next instruction, figure out what that instruction requires, and then manipulate the information in the registers using the ALU. So this is kind of the lowest level of the program that a CPU runs. That's the CPU's algorithm, okay? So that's microprocessor. And nowadays, because of this reason, we take time to travel. There are versions of microprocessor where in the same mechanical package, we also slap in memory also. So some DRAM, some SRAM, kind of all sitting together. In fact, one of the reasons Apple made a big splash with these M processors is that they put the processor together with the memory and all into the same package, and then they are able to put large amount of memory, which both the ALU, whatever the processor can access, and which the GPU on these laptops can access. So some big advantages there. So packaging these things plays a huge role. Next up in integration is what is called as microcontrollers. So microcontrollers take the microprocessor, but then put them with ROM, RAM, IO. So the program is here, RAM is here, a bunch of IO stuff is here. What Apple M1 and some other, I think some AMD processors and Intel processors probably have the same way. They basically combine this part, RAM plus microprocessor into the same package. ROM, where the program is stored, essentially the flash, read-only memory, or a hard drive in older computers, and IO, interacting with these things are largely still handled off the main chip. Okay, but in many applications like your Arduinos and all, you may have a single chip which is doing all of it, in which case it's a single chip computer. So for software, these are our main options. These microcontrollers, as they're written out here, they're often referred to as MCUs. So a lot of lower end systems are made using it. So basically you have everything that a digital system needs, including ADC, analog to digital converter, digital to analog converter, USB ports, radios, stuff like that. A lot of them can be sitting on the same chip. And most computers that you currently buy are really in the form of an MCU. I mean, while microprocessors are costly, thousands of dollars, some of the Intel processors are like that, or NVIDIA chips are like $20,000. But whereas microcontrollers can be like pennies, but most of the digital systems around us are making use of some sort of an MCU. So you can think of it as a highly programmable black box, which has pins, and I can describe the functionality, take bits in or analog signals in, put bits out or analog signals out. And the algorithm we can map using the processor out there and the memory. My algorithm sits in this program memory and maybe some other information, and I can make use of these processors. So typically, companies who make MCU, they end up tending to license it from companies like ARM, which is kind of the major player. And in recent years, some of you may have heard of it, something called RISC-V. It's a processor that has emerged out of UC Berkeley, and they had been kind of in a fight with ARM in a way because ARM was closed source, but now ARM is opening up in reaction to this fight. In fact, just this morning, I saw an email from ARM saying, for educational purposes, they are going to give full access to the hardware code, right? The hardware description language of 3 of their main processors. Previously, they had done it only for the lowest end processor. RISC-V is getting a revival for an interesting political reason also, which is, I'm sure you have heard about the tit for tat between China and US, with US locking down a lot of technologies behind semiconductor things. So RISC-V gives China a way to essentially create processors which are hugely competitive, because RISC-V is all open source. And even the consortium which manages RISC-V now moved out of US to Switzerland, I think. So it's kind of like beyond American regulation directly. But even as a technology, RISC-V is super competitive with ARM, in many ways better than ARM, partly because, much like Linux, a lot of people are contributing to RISC-V. So nowadays, when you buy something, microcontroller, it's probably going to be ARM or RISC-V based. There are a few other players in the market, particularly for very low-end Arduino type things. There are some other players, but for, let's say, mid-tier and high-end stuff, these are the 2 things. And then ARM and RISC-V go all the way to laptops and desktops and even your servers. These chips, depending upon peripherals they have, are often designed for different market segments. So if you want to create a digital system and you're a car manufacturer, there's probably a different line. If you are if you're Boeing, it's probably something different. So there's a rich market, and literally many billions of these devices are sold every year. The reason I mentioned this thing is that as a system designer, you have a palette of things, right? You can implement some stuff here, but you can implement some stuff here, and you can, if necessary, go all the way down to hardware. And one of the takeaways I really I think by the time you graduate, you should be comfortable with all these choices, particularly if you're in computer engineering. This is kind of like a palette of choices, and depending upon what you're designing, you should pick up the appropriate one. So microcontroller, you can think of it as just packing everything into a single chip, which you can now use as a part in your bigger system. So back to that neural network example, I can now implement, so I could have implemented it on these things, right? I mean, if I have a microcontroller, I can literally take analog signals and sort of implement a neural network in software, and then spit out analog values and design something, let's say, which controls, let's say, speed of a motor, for example. Or I could go all the way down to hardware. So now what I can do is, as I was suggesting earlier, each one of these things I can implement into not using a processor, but using some piece of hardware which just does this. So here, uh, sort of multiply accumulate units is what refers to this function. Okay, so kind of the idea is that somehow using a bunch of multiply accumulate units, you add them up, you subject them to this function f, and then you feed it into next layer, and so on and so forth. So very now, where are these multiply accumulate units coming from? Either the chip itself would provide it as a building block, or I can implement these using even simpler logic gates that the chip may provide, AND gates, NOR gates, Boolean logic gates, which we'll see how we can do it in M16. How do we build an adder out of, let's say, simpler gates? But in many cases, the chip vendor itself may provide you some sort of a macro, some sort of a description of how a multiply accumulate unit can be created on the chip. So the chip itself may provide very low level primitives, but much like a software library where someone else writes the functions and you use the functions, same thing with hardware. There are hardware libraries, or often called as core libraries, which basically are little descriptions of how that thing is made using lower end stuff. So I can do this thing in hardware. Why would I want to do it? Anyone? Like, okay, so software is so much easier. I can write program and debug and all. So why do we want to do it in hardware? Like directly going into hardware. Faster. What else? What else do you think? Yeah, absolutely right. Usually faster with a caveat. Okay, so there's a nuance out there. These hardware chips and all usually don't use the latest semiconductor technology because it's too expensive. So your processors, like the M1, M2 processor on our Apple computers, for example, or their counterparts in smartphones, they are high volume products. So they often have access to the latest technology. Like you hear these kind of things like TSMC, 3 nanometer technology and all, and the fight over how America has banned China access to anything lower than 7 nanometer and things like that, right? So kind of how tiny the feature size is in the technology is kind of an indicator of how advanced the technology is, and they're super costly, so only high volume parts. So there is a built-in edge that high volume products, high margin products have. So MCUs and all are probably a few generations behind. And so while mapping in hardware gets you the advantage of customized thing, but it takes away the advantage of technology. In general, though, you still win out. And for the same technology, a good rule of thumb, 10x win going, because you're able to specialize the architecture, you're not carrying extra baggage and all. So so hardware has that advantage. What else? What else do you think hardware can offer?
This kind of goes with faster delays. I mean, you can do a lot of computations in parallel.
Absolutely, and that's, you're right. Part of the reason it is faster is precisely that. It's also lower power, okay, because you don't use superfluous stuff lying around. A processor, on the other hand, whether it's doing an AND operation or an OR operation or an add operation, has this heavy machinery behind it, which is kind of always vigilant and always doing things, right? I mean, so it's a jack of all trades, but then a master of none kind of a thing. Whereas here, you can throw away the fluffy stuff. Okay, so there's a big business out there on creating these application-specific hardware, and a lot of our consumer products, as well as a lot of specialized applications in like defense and space and all, kind of depend on it. So you'll see these chips where now what happens in general is that you may have a processor, like in this case, you see a RISC-V. You may have a whole bunch of simpler processing engines. They may be designed to do things like multiply, accumulate and all. You may then have some other stuff surrounding it, and that we call as our application specific integrated circuit. So kind of the idea is, and you may have some other logic as well. So kind of the idea is that now for my particular application, that's the application specific part, I can create a chip which has just the resources I need. Okay, if I need a processor, I'm going to put it there. If I don't need one, I won't. If I need 16 processors, I have here processing elements, but maybe I need others, maybe I need a different type. I can customize how they are connected depending upon the information flow. So I can basically customize everything over there. And that's called ASICs. And since a lot of applications need it, so part of the challenge is how can we design these things efficiently, systematically, correctly, right? A bug creeping in would be hard to fix because now it is in silicon. It's no more piece of software. It's more difficult to develop. Although it's kind of an interesting thing. So there was a talk I was in the EE department seminar, and this person was making the point that the cost of software development is much more than the cost of hardware development, even though hardware is harder to develop. And the reason is twofold. One, because hardware is so hard to debug and correct a mistake in that we pay a lot of attention to it. And secondly, at the logical level, we implement simpler things in hardware, right? Things which have regular, which are regular in nature, which are simpler in nature. Whereas in software, we do things which often we don't even understand. I mean, a lot of debate around the large language models that you're witnessing in the news media, that how they are hallucinating and bullshitting and stuff like that. I mean, partly because we do in software, we take a lot more liberty, we do a lot more complicated things there. So it's both a function of what we try to do it in hardware. Hardware is complex, both logically and physically. Software is physically not complex, but logically super complex. Okay, so that's kind of the trade-off that ends up happening. So they are both hard in their own ways and require kind of talent. But in industry, apparently, generally, the software always lags a few years behind the hardware in terms of like the hardware gets produced while the software to leverage that still keeps getting done. So it depends on your perspective. One way to think about it is we currently don't know how to write software well for a new piece of hardware. The other way of looking at it is that hardware designers are designing hardware, ignoring what is actually going to make it more easily usable by the software developers, right? I mean, so it depends upon sort of which way you're looking. Okay, so let's see. So one type of, so what's the counterpart of a processor on the hardware side? So essentially what we want is we want to provide the hardware designer with the equivalent of a programming language. So what happens in software? We write code, it gets mapped into instruction set of the processor, and those instruction sets are then executed by the processor. So you can say that really we operate at two levels, right? The programming language and the instruction set architecture. So what are the counterparts in hardware? What's the instruction set and what's the programming language, right? The language in which we express the algorithm and kind of the low-level primitives. So there are many historically. One is something called gate arrays, and this was just still part of the industry. Actually, stepping. So one is I do everything from scratch. I don't care. I mean, I just draw transistors on silicon, literally, right? I mean, everything is under my control. So that's the extreme case, but that really requires a lot of expertise. And even in software, we don't do that, right? We make use of building blocks provided by other people, and then we make our software on top of those libraries. So gate array is an example of that. Essentially, what happens is that someone manufactures a piece of silicon where they put lots of transistors or small functions around transistors like logic functions and or those kind of things. And then you have the luxury of wiring them up. You can't, since the gates themselves are baked in, or transistors themselves are baked into silicon, but the wiring hasn't been done. So what we do is that we wire them up. So your design is really about like whatever algorithm you think, you now have to translate that into a custom wiring of the gates that already exist. Okay. And the kind of the idea is that this reduces time to fabricate because a lot of the fabrication is pre-done and the cost is shared among large number of users. But it does come at the cost of some loss in performance relative to if you were also making the transistors yourself, right? So gate array, so I do transistors and their wiring, that's the extreme case. I rely on prefabbed transistors, I just do the wiring, that's the gate array. Field programmable gate array goes even further. It says that the primitives that we have are no more just transistors or simple gates. They're actually complicated blocks, even entire processors. And field programmable gate arrays basically give you a collection of these, and they give you some interconnect where the wiring is also done. But at selective places in the wiring, they have switches. So again, here, wiring we get to do fairly arbitrarily. Here, wiring is done, but at certain junction points, they have little switches or fuses, which we can configure to connect these macro blocks, as they are often called, into a custom thing. So you can think of it as these macro blocks are like not powerful like processors are, generally speaking, although in some cases you may have some processor also sitting there. They're kind of really simple, but not as simple as like a low-level AND operation or OR operation. It kind of still can do something substantive. And the wiring is already laid out, usually in some regular pattern. A lot of people spend time on what topologies to look at and all, but the wiring is programmable. Okay, and the way it's usually programmed is that at these junction points, they have, like I said, they have fuses or switches, which you can either electrically blow, kind of in some technologies. In other cases, you can write a 0 or a 1 to tell the switch whether it's open or closed. And so then I can configure the flow of information. So that's FPGAs. And in some cases, like I said, they may have other things within it. So like, for example, there's a company called Xilinx, which is very famous for making FPGAs. They have this Zinc series of things where they actually, in addition to those logic cells and all, and some memory, they also actually put processors there. So you can kind of create essentially, these things are already sitting in silicon, it's already fabbed, you're buying the chip, you're designing your own board, putting in there, but the program you're writing in whatever high-level language, it then translates into sending some bits to the wiring and sending some bits to those blocks to configure them. So these are called configuration bits. They are now, it's kind of like a processor, except I'm not dealing with instructions of a processor. I'm dealing with configuration bits of the hardware. And so when the system powers up, it fetches the configuration bit from some memory and then configures itself for whatever purpose you want. So FPGAs have that flavor to it, that you write your algorithm in some high-level language. It translates into a configuration file, and then that configuration file is loaded into the FPGA to give it a specific hardware functionality. Almost sounds like hardware processor, but obviously not as flexible. You're still working at a lower level, but you gain in performance and all. High-end FPGAs can run into tens of thousands of dollars. Okay, they can have billions of transistors, and they can implement hundreds and thousands of millions of complicated gates, and entire processors can be mapped into I think they're called soft processor. So there's a processor running on top, processor implemented on top of an FPGA. That little board I have has a very low-end FPGA in it. It uses an FPGA from a company called Lattice. Now, the reason we pick it is much of this FPGA industry is closed. By that I mean that even the tools to program these FPGAs and load the configuration file, they're all proprietary and they are super expensive. So it makes working with them in an education setting hard. And also the high-end FPGAs, like I said, could be $20, $30, $40, $50,000 just for the chip. Okay, so they can be super expensive. So there is a marketplace for these low-end FPGAs, which are more like $10 type devices with open source tool chains and stuff like that. So they're partly great for low-end digital systems, but also great for education purposes. So we kind of end up using that. So with FPGAs, I can create almost an entire digital system, including hardware and software, all on our own. And so either you can make your own board and put the FPGA there, or you can buy a board like I did, which are called breakout boards or development boards for your purpose, and integrate them. And sometimes these things not only have
Unknown color.
sometimes these things not only have the FPGA and processor and memory, they may also have A to D converter, D to A converter, in some cases, radios even. Okay, so some of the high-end FPGAs can have a lot of stuff on them. So yeah, there's another company called Cypress, which makes something called PSOX, which is again very commonly used in low-end. So that all of this kind of raises the question: what's the fundamental difference between hardware and software? Hardware, the functionality, and by that I mean the algorithm that I'm interested my box to be doing, is implemented via a custom architecture. And we'll see these terms: data path and finite state machine, right? What operations are there in hardware? How do I orchestrate them? You mentioned about concurrence, like a lot of things happen in concurrent manner. How do I orchestrate that? So in hardware, I get to control all of that. In software, functionality is implemented in terms of an instructions that processor runs, and the processor in turn is running a lower level algorithm, which says, like I often said, get the next instruction, execute it, or whatever, get the next K instructions and execute them. So the key difference is in in two regards. One is in how much concurrency. So in case of a processor, if my processor, modern chips often have multiple processors. So like the M1 processor on my thing, I think has 8 processors in it, so it can do 8 instructions in parallel effectively. So, but if I'm designing my own thing on FPGA, I can do many tens or hundreds or thousands of things in parallel, right? So I get to control concurrency in hardware, whereas in case of software that I write on top of a processor, I am limited to whatever concurrency the processor is exposing to me. Usually it's just one. Okay, you write a sequential stuff. And the other one is sharing. Multiple software can run on the same CPU. How do they do that? So thus far, my image was processor gets the next instruction, executes it, gets the next instruction, executes it. And yet we run many different things at the same time on our processors. So what's going on? So those of you who are computer engineers will probably do CS111, which is the operating system course. Essentially, operating system running on processor gives us an illusion that the processor is capable of running multiple things. Sometimes a processor is indeed capable of running multiple things because it has multiple processors, actually. But even with a single processor, I can time multiplex. I can rapidly switch back and forth as needed between different programs. And that's the job of the operating system scheduler. So as it's called, right? It schedules things. So oftentimes what happens is, like right now, I'm running this Keynote program. I'm not doing anything with it. So it's just sitting, waiting idle. It doesn't need the processor. And yet I am speaking and Zoom sharing and all that part is running. So it can kind of rapidly switch back and forth. On the other hand, in hardware, once I decide this piece of hardware is going to do an addition, and that's all it will always do. There is no sharing which is going on, which is obvious. I can't change its personality, and I have to take some specific measures to do some sort of a sharing of that. So multiplexing and concurrency is where hardware and software differ. And as you progress through your courses, a lot of you are first-year students, as you kind of do software courses, think about at least some of the simpler stuff you can actually think of doing it in hardware. And likewise, if you're doing it in hardware, kind of think about what does it mean in software, right? I mean, they're fundamentally two ways of expressing algorithms deep down. There are two ways of implementing, and an algorithm which is efficient in software is often going to be the one which is also going to be efficient in hardware, but not always, because hardware has a different characteristic. So what all of it brings up is, actually, let's do the following. We are halfway through, so let's take a very short break. And to entertain you during that process, maybe the two TAs can just briefly describe what they do. I forgot to ask you guys to introduce yourself, and then we will circle back to this. Okay. So I don't know, Jichen, you want to go first?
So just,
Yeah, just what you're doing research or whatever, something about yourself. Just,
So actually, as mentioned, I'm doing topics related to the FPGA actually. So I'm doing the efficient architectures for FPGA architectures for deep learning as mentioned. So so we follow that FPGA architecture can be efficient. So means it may have lower power and it may run much quicker, have higher throughput for deep learning applications. So that's what I'm doing. I'm just trying to designing such architectures using FPGA. So especially for inference, you know that deep learning. So have two parts. One is the inference, the other is the training part. So I'm doing the and researching other FPGA architectures for inference, for efficient inference, and and the corresponding compilers for that architecture. So if you have background in C languages, then you all know that for languages you have to compare them so that you can run them, right? So actually that's the similar for the FPGA architectures. You have to deploy their deep learning applications using their compilers into their FPGA architecture. So besides researching on their efficient architecture, and also researching on their compilers for their FPGA architecture. That's it.
yes. So actually, just thanks. So just to build upon what Jichen said, so there are two things. Firstly, a lot of hardware now work is being driven by deep learning. Okay, and the reason is because deep learning has become a new type. One way of thinking about it is a new type of way of doing algorithms, in the sense that instead of humans designing the algorithm, the neural network figures out the right algorithm for given enough data, right? I mean, I'm kind of hand waving my way through that, but in a way, it's a data-driven way to describe to write an algorithm, right? I mean, you don't do it from first principles. You're letting the data figure out how to do it. As you mentioned, we kind of train the neural network. That's the training phase, and then we deploy it, and then it's getting new input and producing the output. That's called the inference phase or prediction phase, or right. And sometimes you design hardware for training, sometimes for inferencing, and oftentimes nowadays both, because much like it's not like we were born with a neural network and our brain stopped evolving. We continually learn. So there's a class of systems now which, as it infers, is also learning based upon the new experiences. So that boundary is also often sort of in flux. A lot of people, instead of using GPUs, now are using FPGAs because it gives higher performance at a lower cost. So when you go to these cloud services like Azure or AWS and all, you can actually get access to FPGAs out in the cloud to run things. Of course, now you need to optimize these FPGAs for the deep learning algorithms. So there's a lot of work, including Jichen's advisor, Professor Lei He, sort of who's kind of working in that space. So FPGAs is kind of providing this happy medium between like processor, GPU, FPGA, ASIC. So FPGA is now bringing you closer to kind of the ASIC kind of things, and because they share this software-like flexibility, they kind of lets it do that. The other very important point, which is how, as a user, you approach these things. In all these cases, we have a language, usually very high-level language, could be MATLAB, could be Python, could be C, could be some specialized language for describing a neural network, let's say. And then we compile it, right? We take this language and map it into the instructions or the primitives of my platform, whether it's the instructions of a processor or gates of an FPGA. And in particular, in case of FPGAs, since there's a lot more heterogeneity, like FPGAs come in different varieties, so that compiler chain, which takes you from your algorithm written in some high-level language to this, is in itself a challenging task. So there's a lot of work happening there. The other thing also is when you are mapping it into FPGAs, you often are much more constrained because you have a fixed amount of hardware, and you also have to worry about things like power and also more complicated compilation tasks. So there are people who work in an area called EDA, electronic design automation, which is kind of like the counterpart of people in computer science who work on compilers and all. It's basically, actually, literally other terms that you will see are silicon compilers, behavior compilers. Okay, so these are all compilers on the hardware side of things. Okay, Julian.
Oh, hello again. My name is Julian. Right now, I'm not working necessarily on this at this level of the hardware in projects at this level of the hardware, but I'm originally computer engineering, like my bachelor's degree is in computer engineering, and I specialize on hardware engineering, so I do have knowledge of all this. I work under Professor Mani's lab, the Network and Embedded Systems Laboratory. And my my projects have been, for example, some of those that I've been working right now is, for example, in AI human collaboration, like how do you design these AI agents to collaborate better with humans, understanding that humans have not only like I guess you also need to model the psychological characteristics of human, especially like trust, and this all done in a simulator. So I'm developing that, and I'm also trying to run, design this algorithm to try to train these AI agents in order to collaborate with humans in these team settings. I'm also working in a field called complex events detection, where we basically have this problem where a user wants to detect automatically when a given event happens in the world, like you have a lot of sensors there, and you want to detect something, well, complex, you know, like, I don't know, like if there's, I guess drunk driver, or more. I think a better example is there's someone stealing package at a given location, and it does this in a given time frame that can be like a week. You know, so you want to detect only when this person is stealing package more than 3 times in this given time period. So normal, I guess, methods of doing this, like using a neural network or an algorithm, don't work with these approaches, well, with this setting, because we are dealing again with more large time periods of time, also a very large spatial area. So yeah, you have to create, you have to use what's called a neurosymbolic approach, where you combine both neural methods like neural networks and symbolic methods, which would be like normal algorithms. So that's basically my work, and I also have been working on security in some past projects. But yeah, I guess that's what I've been working. So
Great, thanks. Yeah. So actually, yes, I mean, Julian's projects are an example of the kind of work that goes on in my lab. We basically like to work with embedded computing systems, which are often referred to as cyber physical systems, in that they have a cyber component as an algorithmic component, and then physical as in they interact with the outside world through sensors and actuators. And much of, like, traditionally, the way we used to design these systems was what I would say is kind of the first principles approach. We would understand how the sensor works, how the world works, come up with informed way of designing an algorithm to process that sensor data, the kind of methods you learn in, let's say, signal processing courses and control courses, and then kind of figure things out. What has happened is much like, I mean, I'm sure you know how in computer vision and speech and all, neural networks really are performing much better. Same thing is happening in control and cyber physical systems and all also, which is the way we process these things has changed. So a lot of my lab in recent years, the methods that we employ are, you can say, applied machine learning and all, but working with time series type sensor data with control stuff and all. The project that Julian was describing is something we are doing with US Army, which is a team of robots and soldiers or medics and whatnot, and they are engaged in an operation in a building to do something like, let's say, remove dangerous objects or take care of injured people and all. So the part that we are examining out there is that how do these teams work effectively? They have to sense each other, they have to sense the environment. The artificial agents, the robots in this case, are being controlled by a neurosymbolic. So it's kind of, not everything can be neural network still. You probably never will be, because there are lots of stuff which we either know very well how to do from first principles, and it would be very wasteful in terms of training time and all to do it with a neural network approach. Or alternatively, neural networks work well, but we have very little control over when will they fail. And so oftentimes we surround them with a traditional algorithm. So it's kind of like, again, the ChatGPT type examples, when they start giving out, let's say, undesired content, and also there are what are called as guardrails put around these models. Okay, you make sure that the input is something not bad, like if someone asks a question about, let's say, something which we want to stay away from, a politically sensitive topic or toxic topic of some form, we filter that away. We examine the output, or in another context, let's say you have a neural network controlling a car, you want to make sure it's not speeding, not driving too dangerously close to the car in the front and all. And oftentimes, since these are largely stochastically behaved system, so we kind of still like to surround it by some sort of a guard or some sort of police, if you may, which is kind of making sure, and that tends to be often symbolic. So anyway, those are kind of things that we kind of, among other things that we do, and Julian is kind of engaged in that. Okay, so back to the programming. So, so hopefully I've convinced you there's a whole bunch of implementation choices we have, right? I mean, ranging from general purpose microprocessors at one end to kind of like these application specific ICs and kind of the whole stuff in between. And the question that arises is, how do they compare? So let's talk about speed. So what do you think about speed? Which one would be better? I have an algorithm, I want to run. So let's normalize it. Let's say they are running on this, they're implemented using the same generation of silicon technology. Which one would be faster? Out there, right? I mean, we customize the point we discussed earlier, so you can say speed increases this way. What about power? Or energy efficiency?
Oh, energy efficiency?
Okay, power. I don't know which way the arrow would be, but yeah.
Or it uses?
Yeah.
Oh, and point in the other direction?
Point in another direction, yeah. So for the, again, we have to normalize power to do the same thing at the same rate. That's important, because obviously if I compare, if I'm, let's say, running a neural network, if one network is operating at a faster rate, then it will burn more power. So we have to normalize same technology, same speed. What happens? So power consumption with the microprocessor, because there's a lot of overhead involved, whereas we can have a lean and mean sort of implementation outhead. What about cost? What do you think?
That maybe it does increase as you go down because of what you said earlier about the expensive,
Sure. Okay.
FPGAs.
Okay. Sure. That would be right. Anyone else want to take a stab at that? So that's a little more nuanced story, and the arrows go both ways. Okay, so why do they go both ways? So a little bit out here about how engineering, how we engineer systems, right? When you make something, there is a design cost, and then there is a building cost, right? Per unit, per instance cost. So there is non-recurring cost, which is the capital investment, the designing and all that we have to do, which you have to do whether you make 1 part or 10 parts or million parts. And then recurring is the cost you pay per part. It's the material, the time to manufacture that, the testing of the part and all, right? I mean, so you can say my cost structure looks like NRE plus P times RE. Okay. Now, when we sell these things, then the per part cost is going to be the recurring cost plus NRE divided by P, right? Because I have to share, I'll share the NRE cost across all the parts I produce. So microprocessors have, so microprocessors are more complicated than a corresponding ASIC, just because the corresponding ASIC has less. On the other hand, I produce a lot more of the microprocessor, hundreds of millions of billions, whereas an ASIC may not be in the same case. So now the answer therefore ends up being depending upon how many parts I'm going to be selling. So fixed cost in case of chips include cost of design tools, training cost, how sort of complex the chip was, so how much design time it took, right? I mean, a complex chip or a complex software just takes more design time, more, we have to hire more employees and all. Designing the test routines, and also when you make chips, what chips are made using writing on silicon, so to say, and that is done using a photolithographic process. Essentially, we create masks and then shine light, ultraviolet light, or and then that results in exposure of the silicon, and that's how the transistors are kind of quote drawn onto silicon. And it's a super expensive thing. There's a Dutch company which is pretty much kind of the game in town when it comes to high-end photolithography. We are trying to draw transistors which are tinier than the wavelength with which we are drawing them on. Okay, so it's kind of like, imagine we are drawing a thin line with a pencil whose tip is much broader. Okay, so there's a lot of fancy optics and all which kick in, and these are many tens of millions or hundreds of million type devices. And by the way, again, a key thing in this US-China spat, which is kind of going on because America is trying to prevent those machines from going into China, because that's a competitive advantage there that the West has. Okay, so that's the fixed cost. Then there's a variable cost, the material cost, right? I mean, the cost of that silicon, how many, how big, how many chips I am making. So the way, one of the things we realize is what makes silicon chips so interesting is that we make a whole wafer worth of chip in one go. So this is a wafer, it's basically a disk, usually like say 5 to 10 inch in diameter. Okay, these little squares are the chips. Usually it's the same chip, umpteen copies of the same chip, but there are also other ways of making these where you mix chips from different sources onto the same wafer. Point is, they all share the cost of making the mask, which resulted in this drawing. That mask is part of the machinery, if you may, right? And then these things get built. Then the variable cost is also affected by yield. If I make these things, some of them will be bad because the silicon would have bugs in it, defects in the crystal structure. So the larger my chip is, the more likely, probabilistically, it will face a defect and therefore will be bad. What speed do I get? These are electrochemical, mechanical, optical processes. So all sorts of issues that come in. Cost of packaging, right? I mean, you don't just use the silicon, you package the silicon, you wire to it, and all of that comes into play. So what happens now is that as the volume increases, the non-recurring cost gets shared and goes down because per part. So things which are high volume has that advantage that at sufficiently high volume, things become beneficial. So let's think of, like, let's say I'm making a processor. So processor is very costly. Intel processors can run into many thousands of dollars. But if I'm making only a few systems, then it's better for me to use those, assuming speed was acceptable, than designing my own ASIC, because then I will take the cost of all that mask making and non-recurring. Okay, all that non-recurring cost on my own. By the way, just to put things in perspective, the cost of making these masks and all runs into tens of millions of dollars. Okay, cost of test, the fixed development of test, and also a lot of these things are pretty expensive. So so there's a break-even point, right? So if for low volumes, you may be better off with a processor or an FPGA. FPGA is also very costly. For high volumes, whereas for high volume, they would kill you because you are paying that same cost at for every part you're making, right? I mean, so if I am a Sony making, okay, maybe that's a bad example, Apple making hundreds of millions of iPhones, it's a bad idea to use these things. I would rather make my own chip and optimize it, because I'm selling so many of them that I will come out ahead that way. So that's kind of the idea. So the cost structure for high volume, cost is high with microprocessor, whereas for low volume, cost is high with ASICs. Okay, so that's kind of the story. So the more complicated one, and there are other things also out here. There is also time to market issue. In this industry, if you are late by a month, it may be the difference between, relative to your competitor, it may be a difference between your competitor grabbing all the market. So oftentimes what you also see is that you get the first iteration of your system out using an FPGA or something, even though you're taking a hit on the price structure, but then meanwhile your ASIC is coming into play. So it's just a complicated technical, economic sort of a game that plays. I'm going to skip that. So now when we are creating a hardware system, there are kind of 4 phases that kick in. I have to design it, I have to fabricate it, I have to then package it, and I have to test it. And within each one of these are probably a lot of loops, right? I mean, before you ship it to fabrication, you're probably going to sort of go through multiple iterations. So like you'll have an idea, you'll model it, you're going to do the actual design. So this is where the compilation and optimization of design kicks in. Then you're going to validate it, make sure that once you fabricate, it will work. And this itself is an iterative process. Then you send to fabrication. Fabrication, you kind of make the mask, you make the chip. Hopefully it comes out okay. If not, you're back to design. Okay, so, but nowadays, things are well understood enough that if you send to fabrication, the problem is not that there was a problem in the dialogue out there. The more likely problem is that there was something wrong with your idea or something wrong with your algorithm. There was a bug, as opposed to kind of this part. I think we are pretty good at that. If we model it in simulation before sending to fabrication, then the part which will come back is going to exhibit a behavior very similar to what we simulated. So bugs happen because we overlooked something in our design phase. Maybe our protocol was wrong, maybe our algorithm was incorrect, and so on. Then we package. So we take this wafer, we cut the chips, and then we put them into some sort of a package. Nowadays, there are new forms of packaging which has emerged. So right in our department, there's a center called CHIPS, which Professor Subbu Iyer leads. And what these guys are doing is they take these little pieces of silicon, they flip it, and they put it directly on a big piece of silicon. Okay, so this whole thing is called chiplets. These are chiplets, and chiplets are sitting on a piece of silicon, as opposed to being individually packaged. This has become a hot way of designing systems, and actually the M1 processor My laptop is an example of a chiplet-based system. It has a small number of chiplets, all bonded onto, all kind of glued into, if you may, into a piece of silicon. What happened? Okay, and then finally, once you have done all of that, you test. This can't be emphasized enough. Testing is the biggest time sink and one of the even costlier than kind of fabrication and packaging. Okay, and the reason is the following: if you ship something and then the cost of returning it or a bug happening in the field is pretty tremendous, and you can't fix things on silicon. There is no such thing, right? I mean, well, almost no such thing. So a lot of time goes into how to effectively test, taking into account the fact that unlike software, where I can put breakpoints, I can look into a variable inside the thing here, that's very hard to do. You're limited to testing from kind of a black box, okay? So testing is super critical, and testing is not simply pass, no pass. It's also, oh yes, this thing works, but it only works up to so many gigahertz. So when you buy a chip from Intel, let's say, right, you'll see chips which are same processor, 4 gigahertz, 3.5 gigahertz, 3 gigahertz, right? So what happens is that as part of the testing, they come up with, oh, this chip most likely will keep working up to 3.5 gigahertz. So what we do is we just slap a different part number to it. It's the same chip. We just, because its performance came out, because through the fabrication process to be inferior, 3.5. Some other chip instance, maybe a day later or a different wafer, came out to be better performing, that gets slapped a higher performance number. So testing is also doing what is called as binning. It's grading the chips based on their performance and putting them into different bins so that we can make more money, right? I mean, the other alternative would be to sell all the chips where all the chips are guaranteed to work, but then I leave money on the. Then there is a flip community. If you sort of are into video gaming and all, there is this whole thing on overclocking where people buy a PC and then they cool it and overclock it so that when they are playing games and all, they have a lower latency kind of a thing. That's an attempt to leverage the fact that a chip can work at a higher clock rate if you cool it better. Okay, so so people play those kind of games too. So our focus is here. There are other courses which kind of go into the other three things, but we are into how do we go from an idea to a design which is very likely going to work once fabricated, okay? And what all is involved in that process. So that leads to how do we think of that design process? How do we, a crucial part out here is how do we model a system running our algorithm? So let's see. So there are many, you can think of a system at many different levels of abstraction. So at the lowest level, I can think of a system as a physical system. Transistors, wires, they're built together, connected together at the physical level, taking all the physics into account, resistance, capacitance, and all. The problem with this thing is that the big picture is lost. And also there's too much detail for us to really make any inferences. If I have a bug in the algorithm, this is really very, very low level operation to be working at. Structural is the next level up, where we abstract away the physics of transistors and wires. We don't even think in terms of individual transistors, but we think in terms of logic gates and how they are wired. A lot of what we'll do in this course is at this level, okay? We are not doing this. This we probably have other courses on. Then we combine these things into what is called as register transfer. This is where we begin to worry about functionality at a higher level in a very precise manner and timing. So almost all digital systems are designed using what is called as a clock synchronous way of designing things. That is, there's a clock which is ticking at a regular rate, and operations happen conceptually at a tick. We don't care about in between. As long as when I start an operation at a clock tick, if it finishes by the next clock tick, I'm good to go. So this is called register transfer level, and we'll spend time here also. Then comes architectural level. Here we start thinking about bigger blocks, right? I mean, this is a FFT unit, or this is a multiplier unit, right? I mean, we're thinking in terms of the big functionalities. Architectural blocks, what their behaviors are, how they are interconnected. We are going to do a little bit of this, but this is where you get into M116, for example, which is the computer architecture course. Even above is algorithm. How do we optimize the algorithm? Usually in computer science, people like to think of algorithms in terms of their complexity, right? I mean, so like different sorting algorithms have different complexity, as in asymptotically how the execution time grows. When you're working with chips and hardware, you also have to worry about complexity of area. How does the area grow? How does the memory grow? How does the power grow? So there are different ways of looking at the algorithms and their efficiency. And it's possible that an algorithm which is very efficient on processor may be awful for hardware implementation and vice versa. In fact, part of the success of neural networks is because of the fact that they are very bad for CPUs, because they have lots of concurrent operations, but they excel with GPUs and FPGAs because they are they are platforms with lots of sort of simple hardware. So classical AI, kind of where we reason using symbolic methods and all, was the game in town with CPUs, but even obviously CPUs were limiting, but they at least did better than neural networks because CPUs were better matched to classical AI. But when GPU emerged, and we also had lots of data to train the neural networks, that's an example of an algorithm which matched well with the type of hardware we had. So modeling the algorithm, and in particular modeling how the algorithm will do on our hardware, that's super important. And then finally, when you start out building the system, I mean, I'm going bottom up, but actually we kind of start top down often and kind of come from both way on your team, maybe people with expertise at all levels. So highest level is stochastic, which is we kind of do an abstract modeling of the system performance. Would it do better with neural network? Would it do better with a physics-based model? Would it do better, right? I mean, those kind of decisions. And there you use very high level MATLAB modeling and those kind of things. So when we kind of design hardware, we go through the same thing. We kind of model things very abstractly, then we come up with the algorithms, make judicious, informed decisions at this stage based upon our prior experience and whatnot. And then we drill down. Ultimately, output is transistors and wires at physical level or some such thing. So what this gives us is the following. I have to design a system, let's say controller, whatever, autopilot for Tesla, okay, something like that. So I'll do some sort of a stochastic modeling, high-level system performance, human behavior, the traffic on the road, electric motor efficiency and whatnot. I'll derive specific algorithms from it. I'll map that into the big architectural blocks. What do I need? Then I will decide what goes into hardware, what goes into software. The hardware side, I will do this register transfer, which is clock text level, structural, which is kind of big blocks, and physical, which is actually on silicon. And then maybe some other part of my system will go through source code, instructions, and CPU. And all of that goes into a digital design thing. This paradigm is what is often referred to as hardware software co-design. Almost all digital systems have both elements to it. Okay, no such thing as just the left track or just the right track. If you are an Apple, when you're designing a laptop of an iPhone, this is what you're doing. Okay. On the other hand, I mean, yeah, if you're writing an app for your phone or an app for your application, then you are just doing the right bit. And likewise, if you are just the chip designer, you are doing this. But from a system level perspective, both sides are super important. So when we design systems, you have both of like bottom up approach and top down approach. So oftentimes people sort of make the mistake of going bottom up. which is we start with the lowest level. We kind of start tinkering with connecting things together with wires and stuff like that. And then you hope that the coherent whole emerges from it. It's usually okay for small things, particularly if you are experienced, but it doesn't work with very complicated systems. That's not how we design big systems, that bottom up, the right thing will emerge. So the way we engineer complex systems is that we start with the big picture and we drill it down and refine it and go down, divide and conquer. We divide the system into subsystems with very well-defined interfaces, assign them to different teams with the contract being that interface, and we test at every stage. And the idea is that at any given layer, if the teams below did their job, then when we integrate them, the system must work. Okay, so in fact, probably, I mean, I was listening to a talk once, as well as some naval museum in Spain, in Madrid. I was, I think one of the biggest innovation in human history is our learning how to design complex systems. And a lot of it happened during the when Europeans tried to conquer the rest of the planet, and they needed to make ships in massive quantities, not ship as a piece of art done once and then the next ship is another piece of art designed ground up, but how to fabricate ships in at massive scale. And in fact, a lot of ideas from that. So the talk I heard was that how a lot of divide and conquer, systematic interfaces and all is how the VLSI industry also worked. Okay, so there was a professor, chips in the early era, VLSI chips in the early era were designed like one at a time. And then there's a professor, very famous professor at our neighboring Caltech, Carver Mead, and also his collaborator Lynn Conway. They basically came up with the design process, a top-down design process for the chips, and what tools are needed for it and all. And that's literally kind of revolutionized thing. When I was going through sort of grad school, those were still the early days of the tools and all, and these design methodologies emerging, but it all kind of came out right from Pasadena out here. In reality, there is obviously a mix of bottom up and top down. You don't go purely top down because you do have experience from prior systems, so you know something about what is possible and not possible and all at the lower layers. So at the very least, you have insights from the bottom layers, and some amount of tinkering and all if you're doing cutting edge systems is necessary. But generally speaking, for mass scale system building and all, this kind of a top-down design strategy is what is followed. So this is what it looks like, and I hope to expose as we follow through this and learn about different parts. So we start with a specification, either your inspiration or specific or coming from a customer, and from that specification we go to some algorithm. This thing right now tends to be manual, although you could imagine that other than the most cutting edge of the systems, a lot of these specifications are nothing but a different combination of something encountered in a previous system. And therefore, it's possible, and in fact already begun to happen, that tools can do this thing. And in fact, you could argue that systems like ChatGPT and all are actually capable of doing a lot of that. We hear about how they are doing it coding. And I've already told you that hardware design is no different in coding. So one would imagine that if I can ask ChatGPT to write me a code for, or whatever other equivalent system, I'm just using ChatGPT as to do stuff at that level, it's probably possible for chips also. Okay, so algorithm description. Then we go through high-level synthesis. This is a category of tools which then generate register trust for level language. So algorithm description is where, let's say, something like MATLAB. This is where something like Verilog comes into play. And then we translate that through another set of tools which take this description and gives us a graph of gates and how they are connected. Verilog can express this also. So these are tools which are referred to as logic or RTL synthesis tool. Think of them as compilers at the lower level. This is also compiler, but at the higher level. And then finally, once I have netlist of gates, then I have to just place it on silicon or FPGA, as the case may be. And this is where we do what is called as physical synthesis. And if I have some analog stuff, then maybe some stuff there. For the longest while, analog circuits were viewed as very hard to do, but modern AI tools have begun to create, synthesize very good analog circuits too. So one by one, things which we felt only humans could do are falling, because actually I think we overrate ourselves, in the sense that when we approach design for something, it's really based upon a collection of another permutation of some prior combination. So what we are seeing is that the AI tools have begun to kick in out here, and have begun to kick in for analog stuff, which I mean, not too long ago, we have lots of analog professors in the department that stands for, oh, no tool can ever do this thing. And now, no, the tools are beginning to do it very well, actually, even better than, maybe not as good as the best human, but certainly better than most humans. And that's all we want. So eventually we get the layout geometry, which specifies how things are on silicon, and then we fabricate. But at every step in this process, we continually simulate. So each level, we have simulators. And if we discover a bug in the simulator, we go back up. That's kind of the idea. So, so this is a flow. And in fact, the way I would describe it is, things are pretty mature here in the middle. Okay, very robust tools. Things are pretty good out here. But one thing which has begun to change is that as our silicon technologies are shrinking, a lot of new physics is coming into play. Okay, as in now there's a lot of variations and new physics effects and all. That's point number one. Point number two is, you often hear about like Moore's law, which is how people often refer to the scaling of chips and all, is ending and all. The thing is, we are beginning to see technologies which are beyond silicon. Okay, sort of carbon nanotubes and graphite, and even like people talk about DNA computing and stuff like that. The point is, as the physical substrate changes, clearly there will be an impact out here. And then this part, specification to algorithmic description, is something which was viewed as uniquely human, driven by our ingenuity and inspiration and all. I think this is also falling, okay? Because most of the stuff we do when we go from specification to algorithm description is not new. It's really a collection of our experiences, and as these big models, big AI models are being trained on lots and lots of data, lots and lots of prior designs, and also just like Google system, which won at chess and Go and all, that they learn the way we learn. Okay, so this stuff is also, I think, in a lot of cases is falling, and I think we see kind of the whole thing going on. So I'm going to stop out here for today. What the goal is, in the 89 part of it, yeah, so the goal for this part really is, we are going to spend a few lectures going through these tool chains, Verilog-based things and all, and so that we progress along. If any of you are interested in doing kind of in lieu of the M16 finals, doing something researchy as part of your honors thing, then reach out to me. It doesn't have to have anything to do with Verilog or FPGA or anything like that. It could also be some other aspects of design. If you are particular, for example, there are people exploring how to use these large language models and all to do hardware design. I think that could be kind of a cool project to explore. That can we close a loop? Can we, what quality of Verilog design, how correct they are, and also there are possible ideas. So discuss with me on that. So I want to run this honor section as kind of more exploratory, with kind of the core element being, yeah, just making you familiar with kind of this design process. Okay, so see you in the lecture at 4.